Hey, what's up, guys? Okay, so today I want to talk about another symbol which is also related to the general symbol called the Jacobi symbol. Okay, so hope you guys subscribe to my channel and yeah, so let's talk about Jacobi symbol. And so the idea is that the definition, right, if p is a positive integer, so it's integer positive, and we can factorize it into prime numbers, right? So each okay. And the Jacobi symbol is very simple. The NP defined to be the notation. Let me just use this. So NPIAI. So this is the general symbol, and I from 1 to R. So just the general symbol plus or minus 1, the AI, and the multiply all of them. Okay, and usually define N1 to be 1. Okay. So this NP is either like plus or minus 1 or 0. And yeah, so the idea is that if x squared equals to n mod p as solution, that means that you must have n pi equals to 1, right, for each degenerate symbol, but the converse is not true. So this one, so if you have solution, then the Jacobi symbol will be 1. Okay, but converse is not true. Because even though this guy to be 1, then there will be minus 1 squared. Okay, so this Jacobi symbol can only tell you like one direction. If you have solution, then this guy must be 1. But converse is not true. But it's still give you a way to that if you compute the Jacobi symbol is minus 1, then you know that there's no solution for x squared equals to n mod p. Okay, and so fact, these are trivial that can be done by using a multiplicative property of the general symbol. So MP will be just, so it's complete multiplicative. And you get NP, and you get NQ, you get NPQ. MP equals to MP whenever m equals to n mod p. D is a square NP. A square NP is a square equals to a square NP if AP is 1. Okay, so these are like easy exercise. So basically just the same as the general symbol. Okay, so special formula. So remember that in the previous video that I think in some video that I described the following fact, which is easy to prove. One is that you can use Euler criterion to prove that minus 1p or like p is r prime is minus 1p minus 1 divided by 2. Okay, and 2p can be also minus 1 p squared minus 1 divided by 8. Okay, and so these two are we know. And for the Jacobi symbol, we have the same results, right? So we can consider p just an odd integer. And we have minus 1 to the p, just minus 1, p minus 1 divided by 2, and the 2p. So now this p is like real p, right? It's not forced to be prime, just an integer, minus 1 p squared minus 1 divided by 8. Okay, proof. Okay, so one can write this p into p1 out of pm, small p. And so you can write your p into like from 1 to m, and 1 plus pi minus 1. Oh, so all these p are not to be distinct, right? Just writing it in the prime factorization. So this guy you can write as 1 plus summation I from 1 to m, pi minus 1, and also like I different from j, pi minus 1, pj minus 1, and keep going. And then we know that this guy is even, right? This guy is even. Okay, so that means that this guy is even, right? This guy even, right? Their higher term is even. So if you mod 4, then you get p is 1 I from 1 to n, pi minus 1 mod 4. Right? Because all these are like 2 times 2, right? So all these are mod 4. So you get half of p minus 1 equals to I from 1 to m, half of pi minus 1 mod 2. Okay, so your minus 1p, your Jacobi symbol will be just the product of this. Right, so will be the product of I from 1 to m minus 1 half of pi minus 1. Okay, so this will be minus 1, right? You get the sum over this pi that become large p, so p minus 1 divided by 2. Okay, so hopefully it's a simple proof that you just write down the definition for the small prime, right? Or your general, like the general formula for it, and you collect them. Should not be difficult. Ooh, okay, so now let's consider consider this guy, or in my notation, I use this guy for general p or odd p. Okay, the same strategy. So we notice that p squared is just 1 plus pi squared minus 1. Right, I from 1 to m. And you can write it as 1 plus summation I from 1 to m pi squared minus 1 plus I divided from j pi squared minus 1 and then pj squared minus 1. Keep going. Okay, so we know that pi is odd, right? So this small pi is odd, so pi squared equals to 1 mod 8. Okay, you can, it's easy to check, right? 1 square is 1 mod 8, 3 square is 9, so it's 1 mod 8. 5 square is 25, 1 mod 8. 7 square is 49, 1 mod 8. Okay, so you can arrive p square equals 1 plus summation I from 1 to m pi square minus 1 mod 46. Okay, because all these are 8 by 8, right? So you look at this. And the similar proof, we get p squared minus 1 divided by 8. It's just 1 divided by 8, pi squared minus 1, and the summation I from 1 to m. These are correct for mod 8. Okay, so 2p will be just the products I from 1 to m to p. Okay, I collect everything as a previous proof, so I get p squared minus 1 divided by 8. Okay, and yeah, so these are like two property that amazing true. Okay, but there are more, right? This is, we have still a theorem, so we have the theorem. Basically, we still have the reciprocity law or Jacobi symbol. Right, so recall that in the Legendre one, we get p q p just minus 1, p minus 1, q minus 1 divided by 4. So this proof is very complicated. It has to be proof, right? You can use Gaussian integer or whatever, but not Gaussian integer, sorry, Gauss sum. Okay. And so theorem is that if you take any p, q are odd integer and a distinct, and then also coprime. Okay, then you have pq, qp equals to minus 1, p minus 1, q minus 1 divided by 4. Okay, this means that the Legendre symbol, the Jacobi symbol has the same power as the Legendre symbol. Okay, and the proof basically goes as follow. Right, you can write p into the p1, p2 up to pm, where your q equals to q1 up to qn. And these are all prime, right? So p, q, qp, you just ij, right, m and n. So I from 1 to m, j from 1 to n, and the pi, qj, qj, pi. And then let's call it minus 1 to r. Okay, so these are just using the Legendre symbol, right? These are just pi minus 1, qi minus 1 divided by 4. Okay, so oh, by the way, you need sum over I. Okay, so a very simple proof that you can obviously check is if R is basically I from 1 to m, say from 1 to n, you get half of pi minus 1, half of qj minus 1. And you can easily see that one can like, this is j. Okay, so you can like do the separate, right? Because they are the same thing. I from 1 to m, and j from 1 to n, half of qj minus 1. Okay, so, and we know that this guy, right? This guy, as we previous proved, right? This guy I from 1 to m is half of p minus 1 mod 2. And the same thing for these guys, q minus 1 mod 2, right? So r basically is 1 divided by 4, p minus 1, q minus 1 mod 2. Okay, so we finish the proof. Okay, so I think these are like 3 properties that there's some property that you can use. Okay, so let's work in some very simple example to finish this easy video. So let's say ask 1 AA is whether it's a quadratic residue. Let's sorry for the residue or not. Let's say predict prime to be 1999. So basically x squared equals AA8, 1999 has solution. Okay, so idea using you compute AAA, right? 1999. Idea is that you factorize, right? You compute 4 1999 to 1999 and like 1111999. Okay, and okay, so this, right, these two is just 2 squared, right? So it's 2 1999 squared 1111999. And then we know that 2p, right, is basically minus 1p squared minus 1 divided by 8. Right, so this guy is obviously 1 if p is 1 mod 8. Or 3 mod 8. If p is like 5 mod 5 or 7. Okay, so it's a p is 1 mod 8, right? You get 3. Sorry, p is like 1 mod 8 or 7 mod 8, right? You get 1 if p is like 5 or 3 mod 8, that you get minus 1. Okay, and sorry, this is cube because this is square and this is square and times this, so cube. And I think so this 1999 is basically, okay, so let's see, 1999. If I divide by minus 1, I divide by minus 1 and divide by 8. What should I get? Oh, let's see. Oh, so it's oh, okay. So 1998 just one, sorry, those we got, let's see. So we got 1998 equals to 249 times 8 plus 6. So if I edit, then I get 1999 just 7 mod 8. Okay, so it's minus 1 mod 8. So which tell me that is this case, right? So this 2p is 1. Okay, so that means that this guy is 1. So I can just cancel it. Ooh, good luck. Okay, so I get 1111999. Okay, so I use the reciprocity. So I can use reciprocity. This got me minus 1199911. Okay, and this guy is prime, right? So this guy is prime. So what we can did is that okay, we use quadratic residue, right? So now you can calculate this, right? You can ask whether so basically this ask what? This ask whether x squared equals to 1999 mod 111 has solution or not. But basically you can divide it, right? You can just do the division, right? 111, right? So if you do like a final usual, you can get 1 because you can check 1999 divided by 111, right? So it's 111, 889, right? So it's 8. 8. So got 1, right? Okay. Minus 1, 111. And the 1 is always a quadratic residue, right? So this guy is minus 1. So answer is minus 1. That means that there's no solution for there's this quadratic non-residue, right? Because the symbol is minus 1. So the idea is that we use the Jacobi symbol and prove that 8 is not a quadratic residue of 1999. Okay, and another example. How about like minus 104 is a quadratic residue or not? The quadratic residue or not of prime 997. Okay, so you calculate this. This is Jacobi symbol, and you can separate minus 1. So do the factorization. 2999, 2997, 13997. Okay, and this one easy to compute, right? This guy is like you just check whether it's 1 or formula 1 or formula 3, and the internal of this guy, yeah, we can calculate, right? Just you can calculate, you get 13, right? So in this case, that 9, these are simple, so you get this. Now use quadratic residue, so I can residue it. Okay, so this is a quadratic residue, and I get minus 9 because I can divide it. Okay, these are easy to calculate. Okay, so idea is that you can basically you just use multiplicity, and once you have multiplicity, then you can use quadratic residue, and then once you get quadratic residue, or reciprocity law, and then finally you just directly prove it. Okay, so the answer is no. Okay, see you guys next videos.